Hi, today I'm going to be discussing what valley switching means. And to do that, I'm going to share with you some different switching mode options, show you where ringing comes from, also where to switch, how switching losses improve efficiency, which one to choose, flyback controllers with valley switching, and some definitions you need to know. Hard switching occurs when the voltage across the switching element Q, or basically any FET, equals or exceeds the input voltage. The loss is going to be proportional to the voltage squared. Valley switching is used to minimize switching losses. By turning on Q, or the FET, at a lower voltage, you can improve the overall efficiency. The valley switching uses any of the resonant valleys depending on the load in order to choose where to most efficiently switch. Quasi-resonant switching is using the first resonant valley in order to try to minimize the switching losses across the switch. And last but not least, there's zero voltage switching. In order to achieve zero voltage switching, the output diode needs to be swapped out with a synchronous rectifier controller. The reason we have to do this is with a synchronous rectifier controller, you can tune it so it can allow a little bit of reverse current, so it can actually reset the voltage windings across the transformer, so you can actually drive the voltage across the switch down to 0 volts. So where's the ringing coming from in the first place? When the switching element Q, i.e. the FET in this example, is on, the current is ramped up in the primary side of the transformer. When the switch Q opens, the VDS across the FET shoots up to nearly double the input voltage. During this time, which is called the demagnetization time, this is when the energy is dumped to the secondary side of the transformer. Before the next switching cycle, there's a period, T-res, which is the rest period. This is where the primary inductance and the parasitic circuit capacitances form an LC circuit. This causes a low-frequency ringing. There is no current flowing in the transformer at this time. This is also known as discontinuous conduction mode, or DCM. Quasi-resonant and valley switching controllers leverage the resonant ringing to minimize switching losses. What is shown here is a version of hard switching, but the arrow is pointing at a resonant valley. So where to switch? A quasi-resonant converter, or controller, is closely monitoring the first resonant valley and turning on the switch at the minimum resonant ringing voltage. A valley switching controller switches on whatever valley it detects where it needs to switch. It's doing this in order to optimize efficiency over the entire load range. In deep DCM, the ringing could settle out before the next switching cycle can start. So what about ZVS, or zero voltage switching? This requires the output rectification diode D-out to be replaced with a FET that is controlled with a synchronous rectifier, as with our active clamp flyback controller. This allows a small amount of reverse current on the secondary, which can drive the primary switch voltage down to 0 volts. So why does zero voltage switching improve efficiency? When a FET is hard switched, the time spent in the linear region is a power loss. Here's an example of hard switching where you can see the voltage across the FET coming down as the current through the FET is ramping up. When a FET is soft switched, or ZVS, the VI product is essentially 0. This is why you can minimize power losses. So which one is best for your application? Hard switching controllers tend to have pin-to-pin options and are typically used when cost is the only concern. Examples of this include our UCC28C 4X series and the newer UCC28C 5X series of PWM controllers. The difference between these two are that the UCC28C 5X increased the voltage rating up to 30 volts, lowered the startup current down to 75 microamps, and lowered the standby operating current down to 2 milliamps. But it's pin-to-pin with the UCC28C 4X series. When we released the UCC28C 5X, we also added a new series, the UCC28C 5.6 through 9, which are optimized for SiC FETs. Quasi-resonant controllers tend to be most efficient at high loads. To support light load efficiency, they may have to enter into hard switching mode or support burst modes, which may have audible noise issues. Some examples of these include our UCC 28600 or LM5023. Valley switching controllers optimize efficiency over the entire load range. To optimize efficiency from no load to full load, valley switching controllers employ an AM/FM modulation scheme. You can see the selection table on the next slide. ZVS, or zero voltage switching, can achieve the highest possible efficiency. However, this mandates the extra cost of a synchronous rectifier controller and a FET. Examples of this include our UCC 28781 and UCC 28782. So if you're looking for the best balance between efficiency and cost and power density, valley switching controllers are going to be your best bet. Here's a list of the TI controllers that use valley switching. You can choose whether you want the control type to be constant current, constant voltage, or just simply constant voltage. Do you want to have primary side regulated, which eliminates the need for an optocoupler? The NTC allows you to choose to shut down in case of over temperature. You can choose whether or not to support cable compensation and what kind of offset you'd like to see, whether you want a programmable or a fixed offset. This is useful when you're powering loads that are not on the board itself. The advantage of the high voltage startup is you eliminate the need for a resistor to do the startup, and this actually helps to minimize power consumption because the internal circuitry can shut down the leakage path when the controller is up and running. Also, what's shown here is the different light load consumption of the various controllers and some additional features so you can differentiate the products. So the difference that you see with the UCC 28704 is that it has a constant current under voltage protection, which means if you have a soft short at the load, it will detect that and be able to shut down. Or the UCC 28730 with its ultra light load power consumption does actually work with our wake up IC. This allows you to support a fast transient response with about 1/7 of the capacitance. Here's just a short list of terms to know when discussing flyback controllers. First is primary side regulation, or PSR. This uses information from the auxiliary winding of the transformer to regulate the secondary side. The pros of this: no optocoupler is required. The cons are you can have a slower transient response. Secondary side regulation, or SSR, uses an optocoupler to directly regulate the secondary side. The pros of this is you have a very fast transient response and you are a little more accurate because you are rectifying beyond the rectification diode. The cons are it requires an optocoupler, shunt regulator. The cons are it requires an optocoupler, shunt regulator, and other components in order to support this. An NTC is a negative temperature coefficient resistor. This is used to monitor the temperature of the board, and it can be used to shut down if the board is getting too hot. Cable compensation improves regulation for off-board loads, typically used in applications like USB, where the cable resistance will force a drop in voltage as a function of current. But it can be used in any load where the actual point of load is on a different board connected by wires or over a long distance. Cable compensation can help overcome this effect. When a controller says it has high voltage startup, typically this means there's an internal JFET used for startup. The advantage for this is that you can cut out the leakage currents when the controller is powered via the aux winding, and this can slightly help to improve efficiency at light or no load conditions. Secondary side wake up refers to a special IC we have, the UCC 24650, which overcomes the limitations of PSR control by sending wake up pulses through the transformer. This can reduce the C-out requirements by up to 1/7. At the time of this presentation, this only works with the UCC 28730 and the UCC 28633. Well, thank you for watching, and I hope you know a little more about TI's valley switching flyback controllers.